What is the speed of fluid with viscosity eta flowing through a pipe of length L with pressure drop delta P as a function of radial distance from the center of the pipe R? This is an advanced example, and I'm going to answer it. Actually, the answer, turns out, is already here on the board. It's actually, no, it's this one right here. I was looking at the wrong one right there. And it takes a little bit of calculus and setup to get there, and that's why this is an advanced example. And then what the board goes on to do is actually use this to get the relationship between flow and the pressure drop and all the other quantities that it turns out is equivalent to the model for Poisson flow that we're using with the defined resistance to flow is kind of embedded here in this last expression. Let me go ahead and pull up the answer here just to make things clear. Because this says here, based on the definition of viscosity, the result for speed as a function of radial distance r is this expression. And that's basically that expression written here on the board. One difference, though, is I used r prime here on the board. And what that has to do with is that we're talking about the radial distance r from the center of the pipe as opposed to the inside radius of the pipe, which is really the outside extent of the region of fluid flow. And in this final formula, that's what R means there. But in the math that I was doing here, it made sense to me to kind of make one of the variables put a prime on it. Physicists tend to do that if they have like an R and then they want to call something else R, but they're different. They'll make one of them prime. Anyway, it says here it can be found by solving a differential equation. So all of this, again, there's a lot of calculus going on here. This is, regardless of whether you're in a physics course that's using calculus or not, at least at the lower division level, I would regard doing this kind of thing a bit beyond the level of either of those courses. But to see where it comes from, what I did is I started with this formula that relates shear force of a layer to the fluid viscosity, the area of that layer, the thickness of the layer L, and the speed of the layer. And really, we should think of this speed as being the speed of that layer relative to a layer next to it, and that's going to come up a little bit later how to interpret that. But then what I did is I solved for that speed because my aim is going to get to that expression because that's what the question asked for. And I have this picture here, and this is like a kind of a cross-sectional or view, or maybe kind of from one end view of a cylindrical layer that is flowing through a pipe. I didn't really draw the pipe because I think my talent or lack thereof of drawing concentric circles was already taxed enough for just drawing these two for the layer itself. But I labeled in here that the layer has a thickness delta r prime, and I've labeled this radius of the layer r prime as well, and that comes up in the calculus, having those two kind of, one's the variable and the other one's a small shift of that variable. But based on that, the area that is relevant to the viscosity is really kind of the surface area, sort of the wraparound surface area of this cylindrical layer. So that's equal to the circumference of this multiplied by the length. And the length is really kind of into the page here, so you can't really see it. And unfortunately, my drawing talent was not good enough to try to draw like a 3D perspective on that or something. L being the thickness of the layer, we've redefined to be this delta r prime. And then the shear force F, you might recall from previous example, was that force applied to the layer to keep it moving across like a surface. In this case, I'm going to think of that as the force kind of maybe applied to the inside of the cylindrical layer to make it move with a speed v relative to the fluid on the outside of it. But I've restated that in terms of the pressure drop multiplied by what looks like the area of a circle here, pi r prime squared. So that's really the area of this inner circle here with this defined radius r prime. Now, why does that make sense? Well, the idea is if the net force on that sort of inner cylinder of fluid, and that's like a solid cylinder as opposed to a cylindrical layer, right? The one that we're really interested in. But if we look at just the force on that, there's force on that due to the pressure drop, which would be that pressure drop multiplied by the area of that cylinder. But for that net force to be equal to 0, the force that's pointing in the other direction is really by Newton's third law, that shear force that it is itself applying to the layer. So that's kind of the reasoning I have to be able to equate those two. And I needed to have that to be able to get an expression like this that has V related to that pressure drop. And then it's got these variables r prime and the delta r prime. And so in calculus, the argument we're going to make is we're going to take an infinitesimal limit and say that delta r prime can become a dr prime. That's really going to be like a variable there that we could maybe integrate with respect to, although in this case I think we're looking at it more like a differential equation that we're going to wind up integrating actually anyway. So yeah, either perspective I think works. The V became a dV, and I think that's where the understanding that V is the movement of this layer relative to the fluid just outside of it. So it's not really like an absolute V, and in that sense, maybe I should have called it a delta V in the first place, and that might lend itself to the interpretation that in the infinitesimal limit, like if this layer gets really, really thin, the amount of movement that a really thin layer has to the next neighboring thin layer is going to be an infinitesimal shift, and so hence we can think of that as a dV. And then again, this is now a differential equation that I can integrate both sides, and then that gives me this result. And that again really is the answer to this question, but then it's just a few more steps to go and say, okay, how does that relate to the volumetric flow rate? And for that I had to integrate. Because volumetric flow rate is volume per time, you can also look at that as speed times area, right? Because speed is length per time and area is length squared, so that would be length cubed per time, and that is therefore volume per time. This may be a very simplistic way of reasoning it out, but it works. In this case, though, since in Poiseuille flow the amount of movement of fluid is dependent on that radial distance r prime, we can't just take speed times area. That would work if speed were constant throughout the flow, but it's not. So we have to integrate over that, and that means we need to make that area infinitesimal. In that sense, this area is the area of sort of the cross-sectional area, really, of this layer. In other words, the area that's kind of between these two circles in this picture here, which would be approximately equal to the circumference multiplied by the thickness. Now, if this were not infinitesimally thin, that would only be approximate, but in the limit that delta r prime becomes dr prime, that relationship is perfect, actually. And so that's what I put in there for the dA, and then I put in this expression I just got for V, and then I factored out a bunch of things. And then this is actually a relatively simple integral to do now. So using the power law of anti-differentiation, I think there's a 4 that comes in downstairs. There was already a 2, and that gives us that 8. And you know, if you want to, you could pause this at some point and track all the algebra, but don't feel like you have to. I certainly didn't feel like I had to. And like I said, embedded in there, in this expression, you can see the familiar parts of that resistance formula that is the main piece of information going into the Poiseuille model for laminar flow.